to possibly the simplest one, which is the year. So let's have a definition of the year. It might be, a definition of the year might be for the time for the Earth to do a 360 around the Sun. Okay? Now, is there going to be another one? Remember with the day and the month we found that there were two definitions. One based on the appearance of the object in the sky, one based on the sidereal view, the looking from outside view. And in fact, which one would this be technically? So a sidereal year, if you like, would be that. The time if you were on a different star, miles and miles away, just watching the Earth go around the Sun, 360 degrees would give you a year. Okay? What might be another definition of the year? How long would it take, imagine that's the start of my year where the Sun is in that direction there. How long have I got to wait for it to come back to the same position? It's the same, isn't it? All right? So things are a bit simple with the year. As far as you're concerned, doing GCSE astronomy, there's only one. There is just the 360, okay? Because that is the time it takes the Sun. Does the motion of the Moon affect this? Not particularly, because you don't look at the Moon. All right? So the year is the time it takes the Earth to go around the Sun, and famously is 365, or is approximately 365 and a quarter days. It would be really nice if there was an equal number of days. So, for example, if the year, the time it takes the Earth to go around the Sun, was exactly 300 days. So the Earth went around the Sun in exactly 300 little revolutions of the Earth. Okay? It doesn't. It goes around in close to 365 and a quarter, which means if we just say our calendar's going to have 365 days, the problem is next year, 365 days later, what your calendar is calling January the 1st isn't quite. The Earth has turned an extra quarter, an extra 6 hours. Now, that isn't going to make much difference. Technically, all your clocks are out 6 hours for the next year. But the next year, it'll be out by 12 hours. And then it'll be out by 18 hours. Then it'll be out by a whole day. And if you keep doing that, eventually your seasons will drift out of sync with your calendar. So as you probably know, this is the way we do the calendar. We do it like that, don't we? Every fourth year, we have a 366, which if you average those four numbers, on average, we've allowed 365 and a quarter days. But because we can't really have quarter days in the calendar, we have a fourth day. We have an extra day every 4 years. Okay? Even that's not exactly right. As you probably know, the century years are only leap years if they divide by 400. Every now and then we have a leap second. It's not exactly any exact number. Okay? Now, if I said to you, and this would be quite tricky, you've got a clock. I want you to go outside with a stick and some string and a cup of tea and measure the length of the year. Question's going to be, when do you start and when do you stop your clock? And I would like a better accuracy than to the nearest week. Right, so what you could do would be to do a shadow stick experiment, wouldn't it? You could do a shadow stick experiment and find the time of shortest shadow. How will that be different if you do it tomorrow? Or higher, depending on which season you're in. So the next day, what will happen is it will be a little bit lower, maybe, or a little bit higher. Okay? And what you could do is plot this across the year. There'd be a point in the year, wouldn't there, where you would get the shortest shadow? You would do this experiment and you would get the shortest shadow at midday. The day before, the shadow at midday was a bit longer, and the day before that, the shadow at midday was longer still. All right? Most people, I think, have got a general awareness of this, because if I said to you what's happening to the sun at the moment, you'd be saying we're heading into winter and the days are getting shorter, the sun is getting lower in the sky, the shadows are getting longer, aren't they? Yeah? What do we call this day? This one is called, if you live in the northern hemisphere, this one's called the summer solstice. It's the day of the year when you do your shadow stick experiment and you get the very shortest shadows of all. And the next day, if you do the experiment, you'll get slightly longer shadows. Okay? So you can pick particular days of the year as your key marker points. All right? And as you probably know, after summer solstice, you go to winter solstice. And then the year goes around again. And in the middle, you've got the equinoxes. We talked about these before. You've got the equinoxes in between. And these are the days of shortest shadow. These are the days of longest shadow. and these are the days exactly in between the two solstices, all right? So it's fairly easy to define the year, all right? We looked previously at things like Stonehenge, where the stones are obviously set up not just to look at the length of the shadow, but to mark the direction of the sun. So by marking the direction of the sun and measuring the length of shadows and things like that, you can easily manage your year and your, at least in astronomical terms, your calendar through the seasons, okay? So what we're talking about here is the changing height and direction of the sun every year, which is called the seasons, okay? Now, for the GCSE, you need to be able to explain what's meant by seasons and how they are explained, okay? And it's a nice bit of, effectively, relativity, because there's two ways, I think, of explaining the seasons, okay? One way is the diagram which you can see on the screen, okay? As the Earth goes around the sun, it is tilted. So there's the equator, there's the north and south poles, okay? The Earth is tilted at quite a substantial angle of, from the vertical, it's tilted off by 23.5 degrees, an angle which you need to know, all right? The Earth is tilted relative to, what's this plane called? The plane in which all the planets orbit around the sun is the ecliptic, all right? So you can define, if you like, some people like to call it the plane of the solar system. If you made a model of the solar system, it would be largely flat. It would be largely a flat disk, okay? And all the planets certainly orbit close to the plane we call the ecliptic, all right? The Earth's axis, so if you were explaining this in the exam words to get in, the Earth's axis, that means the knitting needle stuck through the middle of the Earth, about which it spins, the line drawing the north to south pole, is not at 90 degrees to the ecliptic. It's tilted away from that angle by 23.5 degrees, an angle which you need to know. Okay? Now, first thing to remember is as the Earth goes round the sun, it's not like a coring motorcyclist. It doesn't lean into the curve and, of course, lean in the other way on the other side. If the Earth is tilted, as it is on my diagram, it stays tilted. Okay? And this is the reason that we get the seasons. Okay? If the Earth wasn't tilted like this, if it sat upright, then we'd have a fairly boring planet where you didn't get any seasons at all. You just got the same amount of sunlight and night time every single day. Okay? Now let's zoom in on this one. Let's draw it a bit bigger, make it a bit clearer. There's the Earth, it's spinning like that. It's spinning round that axis. The sun's rays are coming in like that. The equator's going to be there, because it's in between the poles, obviously. Okay. The important thing to shade in is the area of the Earth, which is in daylight, and the area which is in darkness. And the important thing to see is the terminator, the line between light and dark, doesn't line up with our spin axis. All right? This is why we get the seasons, is because the line of light and dark produced by the sun is tilted relative to the Earth's spin axis, its north-south spin. Okay? Tell me what it would be like if you lived here. This is very close to the north, or fairly close to the North Pole, so this is northern Sweden maybe, or Norway or Finland or somewhere. Yep. Oh. Excuse me. You wouldn't get any sun, can you see? Because what you're going to do is a little 24-hour circle. Your day is a little 24-hour circle around the pole. Can you imagine that little point turning, like the tip of my finger there, turning around the North Pole? We all turn around the North Pole. This point is very close to the North Pole, so it does a little circle like that. And at this time of year, I think you can see, it never gets out of the darkness. A place here would have 24 hours of darkness. Okay? Well, if you don't like living there because it's too dark, let's go down here. So imagine if you live there, amongst the penguins of Antarctica. What would you have? As the Earth goes round, can you see? You're going to have 24 hours of sunshine. All right. Now, we don't seem to have that sort of weather in Skipton, as you probably noticed. So let's imagine you lived here, which is Skipton. Thank you. What sort of day are you going to have there?
Short day, long night.
Yeah, simple as that. Look, draw the circle. Remember the circle goes around the poles, so it's going to be like that, isn't it? Can you imagine that? Can you imagine Skipton doing that? What season would we call this?
Winter.
Yeah, it's winter, isn't it? All right. This, on your diagram, if I've drawn it the right way round, this would be northern winter. Because the pole of the Earth, the North Pole, is tilted away from the sun. Simple as that. The North Pole of the Earth is tilted away from the sun. And that means the area, or the half of the Earth that's in shadow, is much larger in proportion up here, much smaller down there. All right? It's because the spin axis and the spin axis and the light-dark line are at an angle to each other. Okay? I won't draw the other one, because it's just too boring. But I'll leave you to work out why that, pretty obviously, is northern summer. And the key thing there is obviously to draw in the light and the dark. Okay? 6 months later over here, we have northern summer. And if you can imagine living in Skipton here, let's just put Skipton in. What are you going to get? A little bit of darkness. And a great big chunk of your 24 hours is going to be daytime. Yeah? And that's pretty obviously summer. If you live in the southern hemisphere, as you know, if you've got relatives who live south of the equator, their seasons are flipped round. They have their seasons the opposite way round to us. Here, the North Pole is pointing away and the South Pole is pointing towards. Here, North Pole towards, South Pole away, hence northern winter, northern summer. Okay? Notice a couple of other things. Firstly, tell me about this distance, which I've drawn badly actually. The distance between the Earth and the Sun. We know quite a lot about orbits now. We know about things like Kepler's laws and stuff. What do you know about the Earth's orbit around the Sun? Yeah, the Earth's orbit around the Sun is an ellipse, isn't it? Or an oval. Which means sometimes it's slightly further away and sometimes it's slightly closer. Very important to remember that the effect of distance has nothing to do with the seasons. All right? And in fact, if you look at it, it's actually the wrong way round. I've drawn mine very badly. I think in northern winter, the Earth actually comes to the point where it is closest to the Sun, called perihelion. Good homework would be to look up the date of the Earth's perihelion. I'll tell you something, I'm pretty sure it's in the winter. I'm pretty sure it's in December. All right? The Earth's aphelion, the point where it is furthest from the Sun, I'm pretty certain is in our summer. All right? And you think, well, that's mad. The Earth is closer in the winter and further away in the summer. And that's because this difference is very small. All right? Very important idea. Excuse me. Start again. Seasons is to do with the tilt of the Earth. It is not to do with the distance. All right? Knowing a little bit of GCSE astronomy is potentially a bit confusing because you think, oh, season, it's obvious because it's an elliptical orbit. Sometimes it's close, sometimes it's further away. That's absolutely true, but the difference is really small. And if I say to you what actually is a season, how do you know if you fell asleep for many months and you woke up and want to know what season it was? You'd look at things like how long the sun was in the sky, how high the sun got in the sky. I mean, Skipton, it's cloudy all the time anyway. Yeah? Is it just to do with temperature and brightness of sun? Really? How do you know it's summer? Because the sun's really high in the sky, isn't it? And it spends a very long time there. How do you know it's winter? The sun is very low in the sky and doesn't spend very long above the horizon. Okay? So very importantly, although the distance does change and the Earth has a perihelion and aphelion, that is not the cause of the seasons. The seasons are caused by the tilt of the Earth. Okay?